Hello and welcome, everyone. I'm delighted that you've all been able to join us. My name is Bill Flanagan. I'm the President and Vice Chancellor of the University of Alberta. And I've been watching the chat and everyone joining us from all over Alberta. I see we've got snowbirds joining us from Arizona. This is a wonderful opportunity to get together online. And by doing tonight's event online, what we've really been able to do is extend the reach of the President Speaker Series. And so we have well over 500 people who've signed up to join us this evening. So I just want to extend a really warm welcome to all of you. Before I go any further, I'd just like to take a moment to acknowledge that the University of Alberta is located on Treaty 6 territory and respects the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. And tonight marks the fourth in the President Speaker series. And this has been designed to try to share some of the tremendous research happening at the University of Alberta and to meet some of our researchers and learn more about the research that they're doing, the impact that this research is having in Alberta, Canada, and around the world. And one of the great joys of being president is that I get to meet such talented faculty, staff, and students at the University of Alberta and learn about their research. And one of them is Dr. Amit Kumar, who's going to be joining us this evening. And Amit is a world-leading expert in climate research and in energy research, and particularly in hydrogen. And I've had an opportunity to travel with Amit. We've been to India together, and great opportunities for me to ask him a million questions about energy transitions, energy futures, and also hydrogen, in particular, how Alberta can play a key role in energy in the future going forward. As you know, of course, the University of Alberta has long been an energy research powerhouse, developing the research that enabled Alberta to develop its energy sector, including devising the way in which to remove oil from the oil sands and giving rise to a whole birth of a new energy industry in Alberta. And the University of Alberta remains very engaged in energy research in support of Alberta's energy sector. And one of our top researchers in the field is Dr. Amit Kumar. And just a little bit about Amit. He is a very highly respected professor at the Faculty of Engineering. He oversees a large team of postdoctoral graduate and undergraduate researchers. Amit is a Tier 1 Canada Research Chair in the Assessment of Energy Systems, the Synovus Energy Endowed Chair in Environmental Engineering, and the Deputy Director of U of A's Future Energy Systems. He's also the Associate Director of the NSF Global Center for Sustainable Bioproducts. He's a very busy fellow. And his research to mitigate climate change, specifically to reduce greenhouse gas emissions, has been recognized worldwide. He's a sought-after resource, having advised a number of provincial, national, and international panels. Amit's been recognized by Reuters in the list of the world's top climate scientists, and we're enormously proud to have him here at the University of Alberta. So following Amit's presentation, he and I will have a conversation where I get to dive deeper into his research and ask him a few questions, and some of which were pre-submitted by the audience. And so without any further ado, over to Dr. Amit Kumar.
Hey, thank you, Bill, for the kind introduction. Good evening, everyone. It's a pleasure to be here. I give seminars and presentations all the time, but to talk to an audience which is as diverse as you, it's about energy system is exciting, but as well as challenging too. See, about 25 years ago, when I started working on energy systems and its assessment for decarbonization and different decarbonization pathways, there was interest, but it was not a priority at that time. Most of the discussions and work were in silos. We talked about one part of the energy system, not the other. At that time, there was limited focus on countries considering an energy systems approach. And then using that, for decision making. Fast forward 25 years, look at now. I mean, we talk mostly about energy system, look at things through a lens of energy system. So today we're going to talk about energy systems. What I plan to talk about a little bit is in terms of overview, in terms of bringing everybody same page in terms of what do we mean by energy system, where we are, and then a little bit in terms of the need for energy system changes, why we are doing it, what drives it, and then give a couple of examples of the work that we have been doing over the decades on this, and then end with key takeaways and have some discussion as Bill talked about. So if you look at energy system, it's basically consists of different pathways. And I would say that it starts with the energy resources available. We use these energy resources to produce energy. So for example, extraction of bitumen or crude oil, using natural gas, extraction of natural gas, using these resources to produce energy. So we produce these resources, transport it through different modes, pipelines, rails, trucks, ships, you name it. We transform it, convert these fuels to electricity, oil to diesel, wind and solar-based power. Again, transport these resources to the consumers who use it. So, and then utilizing these energy sources for lighting, cooking, transportation, and so on. So this whole chain that we have from the resources production all the way to utilization, everything is part of an energy system. If you look at energy system, and this is all the activities that you do in terms of starting all the way from production to utilization is associated with impacts. Greenhouse gas impact, a lot of focus on greenhouse gas impact, water impacts, land use impacts, and others, including, let's say, for example, the biodiversity impact. Now, if you look at the energy system change or energy system transition, what does this mean? It means basically moving from one type to another type. So if we think about production, for example, we look at fossil fuel-based furnace or fossil fuel-based energy being replaced by renewables or low carbon intensity energy, for example, coal by natural gas. So, from one energy source to another energy source. On the consumption side, so fossil fuel-based furnaces, so for example, natural gas furnaces being replaced by electricity-based furnaces. So again, change from one source to another source. Transportation sector, electric vehicles, basically coming in and replacing some of these gasoline vehicles. So again, change from one source to another source. So that's kind of the energy system change. But this change is continuous. It's a journey rather than a destination. And the energy transition has been happening since the beginning of the civilization. We have transitioned from non-commercial energy to commercial energy. For some part of the world, it is the transition from one fossil fuel to another fossil fuel, much cleaner, fossil fuel to renewable fuel. And then in some jurisdiction, it's even just having no energy to energy. I mean, if you imagine, like in 2022, there were 600 million people in the world who did not have access to electricity. So getting electricity is a transition from no energy, no electricity to an electricity source. So it's a journey rather than a destination. That's the key message here. Now, if you look at the need for the change, a lot of focus on greenhouse gas emissions and basically to mitigate global warming. That's one of the key drivers. But the other drivers also is on energy independence and then availability of the energy sources. If we look at just the focus on the greenhouse gas emissions, I mean, from 2005 to 2022, our GHG emissions have increased 20%. From 45 billion tons of CO2 to almost 54 billion tons of CO2 now. We still use significant portion of our energy, which comes from fossil fuels. If you look at the way we are going, our global energy consumption is increasing. Today, we have about 8 billion people. And we expect by 2050 would be somewhere between 9.8 billion to 10 billion people who will need energy and who will need energy on larger scale. And a lot of these would be still supported by the fossil fuel sources, and which will lead to GHG emissions. So need to mitigate this, again, drives a lot of these changes. Energy independence, and this is focused on energy is not available globally everywhere that we use energy. So it is concentrated in certain jurisdictions. So, for example, the fossil fuel is available and provided by 21 countries only out of 190 countries, more than 190 countries globally. It needs to be transported from one place to another place. There are challenges in terms of the geopolitical issues whenever there is disruption in the supply chain. If you look at some of these fossil fuel production places, 75% of the coal is only produced by 4 countries in the world. You look at crude oil, only 6 countries in the world provide 60% of that crude oil. Only 6 countries provide the amount of natural gas, almost 60% of the global natural gas consumption. So there is transportation, and these are impacted a lot by the geopolitical issues. And so there is focus on producing what we have within our jurisdiction, where we have control. So again, getting to energy independence is a drive for change from one energy to another. And then these are availability of the sources in terms of the renewables, what is available there, what sources are available, low carbon intensity fossil fuel which are available. The resources for the coastal countries, these are some of the resources in terms of the wave and tidal wave when it becomes cost effective, but these are potential sources. In most of the cases, the drive is to get energy at lower cost. So we'll focus a lot on GHG mitigation and then the decarbonization pathways. In terms of GHG mitigation, when I think about the pathways for decarbonization and the ways to mitigate greenhouse gases, I typically focus on and categorize all these options into 3 key baskets. The first basket is energy efficiency, where you improve the way you use energy. The second option is using more renewables, renewable sources like solar, wind, biomass, geothermal, in place of the fossil fuels. And then the third piece is more focused on capturing what we emit. So for example, we use natural gas for producing power. You capture that CO2 which is emitted and put it underground or under the sea. So sequestering that CO2 which is emitted. And then the other piece that I also put hydrogen, there's a lot of interest in hydrogen. Basically, it's kind of, it could be placed into both the baskets because the way you produce it, you can produce it from the renewable sources like wind, solar, electricity from those sources, and you can use that in an electrolyzer to produce hydrogen and oxygen with water going as a feedstock. You can also, and what we do today is produce a lot of hydrogen from natural gas, but then adding carbon capture and storage to this to produce blue hydrogen or low carbon intensity hydrogen. And we'll come back to this. So if we look a little bit deeper into energy efficiency options, now we have demand sectors, basically these sectors which consumes energy. So our household, our offices, industries, they all consume energy. And there are lots of options of improving the energy efficiency for these. So under this basket of options, you have a lot of these energy efficient, for example, our residential sector, efficient lighting, cooking, heating, appliances, and so on. Industrial sector, and this is just a snapshot of some of the key industrial sector here, but improving the efficiency of the equipment that we use, improving the efficiency of the way we use energy. So thereby reducing the amount needed and then GHG mitigation. Transportation sector, both freight and passenger, basically focuses on in freight sector efficient trucks, efficient trains or pipelines. Passenger transport focuses more on the cars, efficient cars. And then the other sectors, similar to like, other sectors in terms of improving the efficiency. The demand sector, but at the same time, we also have these energy efficiency options for the supply sector. So efficient power generation, power generation from the boilers, efficient turbines. So these also provide lots of options. Most of the energy efficiency options are the low-hanging fruit. Basically, those are lower cost, and you can basically adopt that in terms of the lower cost per unit mitigation, per unit CO2 mitigation. So this is the first basket of options, and there are thousands of options to mitigate this and to use this. The second one is the renewable energy implementation, and I categorize these into two baskets of renewable. So one is the intermittent, which is not always available. So wind, whenever wind blows, we can generate power. Whenever there is sun, we can generate solar energy. Same for tidal, but these are intermittent, not always available. But then the other basket is in terms of the base load renewables. So you have hydropower, biomass energy, geothermal. These you can use all the time. So these plants can run all the time. And these are base load renewables. And then I also put in here nuclear energy, because there is a lot of interest in nuclear energy and actually using nuclear energy as a decarbonization pathway, because you don't have GHG emissions when you use nuclear energy. We have been using nuclear energy on large scale, but there is a lot of talk now about small modular nuclear reactors. So these are 1/3 the capacity of larger plants, about 300 megawatt. Just to give you a perspective in terms of our Western Minton Mall here uses 25 megawatt of electricity. So you could see in terms of how decentralized these reactors are, the small modular nuclear reactor. These also are smaller in size, footprint, but it also is, you can build these components of these and ship it. So it's easier to assemble, and that helps in reducing the construction cost. These modular reactors also have benefits in terms of how frequently you need to refuel this. So typically, in a large nuclear power plant, you will refuel it in 1 to 2 years. These you can go to 3 to 7, and there is effort in looking at refueling this every 30 years. So you could see the impact of these. This technology is still developing, but this also is a key option for decarbonization. The third basket I talk about is in terms of the carbon capture and storage. So whatever we emit, we capture that and put it underground or undersea, depending on where we are located. But this is referring specifically to capturing the emitted CO2. And then under this also you have carbon capture and utilization. So the CO2 that is emitted, you capture that CO2 and then utilize for producing fuels or materials. So again, that helps in sequestering the CO2. So we covered the 3 baskets, and then thousands of options of decarbonization in these 3 baskets. The last one here that I want to talk about is the hydrogen option of decarbonization. If you think about hydrogen, hydrogen is the lightest element. It is most abundant element after helium available globally. It is colorless, odorless, tasteless. It burns in the gaseous form, but it produces water when it burns. It's available in vast quantities in form of water. So you look at oceans, rivers, ice packs, all have hydrogen. We use a lot of hydrogen today here and globally, but this is produced from natural gas. We produce hydrogen from natural gas, and then in the process, there is emission of CO2. But currently, most of these CO2 goes into the atmosphere. And the process that we use is the steam methane reforming. That's what we use it for producing hydrogen. But this is gray hydrogen. Another key basket is in terms of producing green hydrogen, which is from the renewable sources. So we produce electricity from these renewable sources. use it in an electrolyzer, and produce hydrogen and oxygen with water as a feedstock. Most of these, almost all the renewables can produce electricity and then produce hydrogen through electrolyzer. Biomass could be used directly to produce hydrogen through gasification and pyrolysis. And here biomass I'm referring to, for example, waste residues, straw, for example, forest residues. And then all the natural gas-based hydrogen where we add carbon capture and storage, those are called blue hydrogen and low carbon intensity hydrogen. And there are a number of these different technologies, how we can produce this. The advantages of these range of technologies, the extent of GHG mitigation that we produce, and the form of carbon that we produce. For example, steam methane reforming, we can get up to 52 to 60% of CO2 mitigation. And then, the cost impact comes in. Autothermal reforming, which is a newer process, but it could get up to, say, 95% carbon capture storage. And so, for example, natural gas depolymerization produces CO2, but also produces carbon in solid form, so which is easier to handle. So a number of these processes are there, but this is called blue hydrogen. So to bring all this back in terms of you have 3 baskets of option and thousands of these decarbonization pathways, and the challenge comes in terms of how do we choose this? How do we make decisions on these decarbonization pathways? What gives us the best bang for the buck? And this is the question that we are trying to answer. And before we go there, I also want to point out that there is also a significant move and an effort in terms of producing sustainable materials, which will basically help in all these decarbonization pathways, but also help us in reducing our GHG footprint. So sustainable materials is a key piece of work too. So research focus, especially on the modeling side, what we have been doing for a long time. In 2006 and 7, this is the first kind of Sankey diagram that we developed at that time. The focus at that time was to just understand, what resources we have, what we use these resources for, and where does it go. So here, I don't want you to focus on the numbers. The key here is in terms of looking at the column. So here, what you see is all these different sources that is available in Canada. This is a Sankey diagram for Canada for 2022. So this is based on actual energy production and consumption. So these are all the sources that we have. In the middle is all the transformation of the primary sources to secondary sources. So for example, natural gas to electricity, crude oil to gasoline, diesel, and so on. And then here you have basically all the demand sectors, so which consumes energy. So you have residential, commercial, transportation, industrial, and so on. The other key piece for these Sankey diagrams is that the width of each of these arrows gives you a sense of the extent of energy intensity. So here you see oil, and crude oil export, major source, and major energy activity in Alberta and in Canada. So we export a lot of crude oil, natural gas, nuclear-based electricity is another key one. So this is the Canadian version, and this is, you see, a part of this is reflected in the Alberta's Sankey diagram is crude oil, a lot of these, and predominantly this is mirrored in the Canadian form of the Sankey diagram. What you don't have here, you see, not a lot of nuclear, which is a potential option for us. Minor contribution of hydro, which is major ones in BC and Quebec, and Manitoba too. And then some of these, our major industrial sector, a lot of natural gas consumption in the oil sands sector. So from here, you look at these resources, these pathways for decarbonization, and then we need to find a way in terms of how do we address and assess these different decarbonization pathways to make decisions. And this is where kind of a lot of challenges comes in terms of decarbonization pathways. The very first one is in terms of the perspective that we have and differences in energy exporter or energy importer needs. So jurisdictions which are net energy exporter, for them, these fossil fuel or these sources which are GHG intensive, they are bread and butter. They are the source of livelihood. So how do you transition? At what rate do you transition? From an energy importer perspective, and so for energy exporter, Alberta is an example. Major contributor of GDP comes from oil and gas sector. So the challenge is in terms of how do we transition, and at what rate, keeping in mind that it is a key source of bread and butter for us. Energy importer perspective, we look at, for example, Germany, big manufacturing sector, they import energy. And for them, the perspective is more on what form of energy do we import which can help us in decarbonization. So it could be in form of LNG, or it could be in form of hydrogen, much cleaner source. Similar to this for Asia Pacific countries, Japan and Korea, net importer of energy, and where the options for decarbonization is not a lot, not available there. There are, but the challenges is in terms of decarbonizing that, capturing that CO2 or sequestering that. There are challenges in their geology, so they have to export this CO2. So again, the key is in terms of the perspective and the challenges for an exporter and an importer. That is very critical. There is also challenges in terms of really developing and understanding the novel technologies and their characteristics to assess these. And that's an important piece, because you need to have these characteristics developed to ultimately determine what is the best pathway, what is the cost associated with that, or the GHG footprint. The other one is in terms of having the credible databases for baseline technologies. And that's always a challenge because it changes from one jurisdiction to another jurisdiction. It changes from how you have developed those data. So again, having these credible data sets. We do use a lot of word, and you see a lot of focus on life cycle assessment and techno-economic assessment. Life cycle assessment basically helps us in looking at the environmental footprint. A lot of focus is on GHG emission footprint. Techno-economic assessment helps us in assessing the cost. The challenge is that if you do life cycle assessment, a lot of focus is on the environmental footprint, and then the cost footprint gets missed. If you focus a lot on the TEA side or techno-economic assessment, then you miss there's a lot of focus on the cost side, but not on the environmental side. And so the challenge is in terms of integrating these two. The other key piece comes in is in terms of, newer technologies coming in. In fact, we don't even know if all the technologies would be available, which will help us in getting to net zero, or the future technologies. So, and the technologies which are now being developed, those are at a smaller scale, lab scale, or pilot scale. The challenge comes is how will this progress? How will this penetrate into different sectors of energy, energy sectors, energy demand sectors? What would be that profile? How do we see these in 2035, 2040, 2050? So developing and understanding the penetration of these technologies in these different sectors is a challenge again. And then the focus on GHG emission only. A lot of focus is on GHG emission, but other environmental impacts, which are critical. And specifically in terms of now, we talk about hydrogen. There is also, any of these green hydrogen needs water. So needs to look at the water availability in different jurisdictions. But that's also a key challenge. So what we try to do is, and we have been developing this approach of integrated assessment over the years. And I showed you the Canadian energy system and that diagram. What this represents is the Canadian energy system, but in form of the data-intensive model which we have developed over the years. What you see here is in terms of, you have a lot of these different provinces, different resources that is available. You have different energy transformation. You have different sectors of energy. And then you have where we use energy actually in different sectors. So for example, residential, space heating, water heating, appliances, and so on. What form of energy we use? So what we have been trying to do and have been able to do is develop these data intensive model where we go into details of each and every equipment and then try to understand the energy intensity, the emission intensity of this, which also helps us in looking at then developing these thousands of scenarios in terms of replacing a technology. What is the impact on the whole energy system? So you're not doing it in isolation. We do this, so this is kind of, the whole energy sectorial model, but this is supported by a lot of work outside of these Canada-based model, where we try to look at separately understanding each of these technologies through development of detailed process models. In terms of estimating the cost, developing these techno-economic models, a lot of technology penetration models, using a lot of techniques, machine learning techniques, to basically try to support the scenario development. I'll give a couple of examples which we have done, and there are numerous of these. So we looked at a lot of these works on the potential for energy efficiency, and energy efficiency, how much can it mitigate? Some of our estimates suggest about 24 million tons that you can mitigate through improvement in energy efficiency in Canada. What this shows is now bringing everything to the same page. So what you have is each of these colors that you see is different sectors. And each of these colors and different sectors is a thesis in my term. So you have students working on these thousands of different options. And what we show here is that the width of each of these bars shows the extent of mitigation possible by implementing a particular technology. And then the y-axis shows the dollar per ton of CO2, showing the cost effectiveness of these technologies. So all that below the horizontal line are very attractive. So a lot of energy efficiency options are low-hanging fruit. The other example I'm going to give is quickly in terms of the hydrogen opportunity. So we do have a lot of hydrogen production already going on in Canada. We produce about 4 million tons of hydrogen. Most of these today, we use it in the Western region for oil sands upgrading and then for producing chemicals. But this provides a lot of opportunity in terms of having a lot of resources to produce these hydrogen, having the experience of producing it on a large scale. So we currently have large scale plants which are 350,000 tons of hydrogen production each year, which is a very large scale plant. We do have capacity in terms of producing these with low carbon footprint because of our carbon capture and storage infrastructure in Alberta. And then trained workforce who have been handling and producing hydrogen. So it's a lot of different ingredient which comes in and provides economic opportunity. See, we have been using hydrogen, but a lot of focus now is using this in different sectors. Wherever you use natural gas for producing heat, you can use hydrogen there. And so in our residential home, we could have hydrogen furnaces, in offices, in industries where you use heating application using natural gas, you could use hydrogen. It could also be used in high temperature applications, transportation sector, heavy duty trucks, power generation. But then another big opportunity is in terms of exporting it to the jurisdictions who don't have a lot of options for decarbonization. Asia Pacific countries, one example. The other aspect of our modeling has been in looking at the water impact of these decarbonization pathways. So we have been developing these data intensive models, which helps us in, assess the impact of a decarbonization pathway, but in terms of water. How much water would be needed? What is the water footprint of a particular decarbonization pathways? So that's kind of a snapshot of the type of work that we do in terms of integrated assessment. I'd like to summarize here in terms of, again, emphasizing energy system change, energy transition is a journey, it's not a destination. We have lots of options, typically in three baskets: energy efficiency, renewables, and carbon capture and storage. And the GHG mitigation needs to be taken, and the decision-making needs to be taken only after looking at all of these decarbonization pathways. Hydrogen provides bigger opportunities. Nuclear is another big opportunity for us in terms of decarbonization. and especially the newer technology in terms of the small modular nuclear reactor, there is need to do integrated assessment. So again, looking at the whole energy system perspective and all these decarbonization pathways. And then not only GHG emissions, but other impacts needs to be taken into account. I'd like to acknowledge a lot of these funders over several years and decades, how they have supported the program and trained more than 200 HQPs. And I would end at this point, and thank you for your attention and attending this. I'd look forward to the discussion.
Great. Well, thank you, Amit. I really enjoyed your talk. And first, I want everyone to know I'm wearing my U of A swag sweater here, which I think is available in our bookstore. So I'm wearing a green and gold for tonight's conversation. But first, Amit, I just want to mention we had some great news today. With the NSF Global Center for Sustainable Bioproducts, your funding was approved. You will receive 2.5 million from the federal government, and this is a 5-year initiative. And I wondered if you just might want to tell us a little bit about this new Center for Sustainable Bioproducts.
Okay, so there are two pieces to it. The Global Center for Sustainable Bioproducts, it's a 6-country initiative. So, we have been working a lot on the biomass side and using biomass for different purposes. We do produce biomass-based composites and polymers. The challenge is in terms of their strength, in terms of their biodegradability, and then in terms of how we produce it. So this is a collaborative effort between 6 countries led by US, Canada, UK, Japan, Finland, and South Korea. And this is more than 10 different universities are participating in this with several industrial partners. And what we want to focus on is in terms of look at developing these polymers and composites or bioplastic using biomass sources like straw, for example. If you look at straw today, in prairies, in fact, we have 16 million tons of straw available every year. Most of these are left in the field to rot. So is there a way to use these? We have lots of forest residues which are burned on the roadside during logging operation to prevent forest fire. Are there options to use these to produce these biopolymers or bioplastics? So the effort here is a global effort in terms of developing technologies and to produce these sustainable materials.
Yes, and I've had the opportunity to tour your lab where you're taking residue from fields and turning it into a slurry and developing techniques to transport that. Maybe you can tell us just a little bit about what you're doing in your lab there.
Yeah, we have been working on biomass utilization for a long time. One of the key challenges in biomass application, and for folks, when we refer to biomass, we are looking at a straw, for example, or forest residue or wood chips. That's what we are referring to. One of the challenges, and biomass has been used for generating power. We do it all the time at pulp and paper mills. They use those residues and produce power, or for producing heat. But one of the challenges is in terms of the scale of operation. Now, if we go outside the mill, like, for example, a straw, let's take a straw as an example. If we want to use that straw to produce fuels and chemicals, most of these, actually, there is not a large commercial scale plants available. And even if there is some operation, these are a small scale operation. One of the key challenges is biomass supply and logistics. So in terms of supplying biomass, transporting biomass, most of these is done through trucks. And the challenge is in terms of the cost of delivery, dollar per ton. What we are trying to do is, how do we increase the scale of these operations? So how do we transport large scale biomass in form of a slurry? And then through pipeline, what pipeline can do is it helps us in reducing the cost of transport, so dollar per ton material transported. It could help us in getting to a larger scale, so you could get economy of scale benefits in the conversion facility. So ultimate goal is to reduce the cost of these biofuels, reduce the cost of these biochemicals. And this is one of its kind lab that we are trying to work on, where we have designed the pipeline to transport the slurry. And so the aim is, again, that is one of the decarbonization pathways, using renewable product, a renewable feedstock to produce these energy and fuels.
Yes, and one other interesting research project we've developed at the University of Alberta is CANSES, the Canadian Net Zero Energy Solutions. And this is an energy project that is focusing on hydrogen, and I want to chat with you a little bit more about hydrogen, carbon capture, storage, and utilization. Also, energy grids, critical minerals, and water and land reclamation. And the website is up there. And for those of you who are interested in learning a little bit more about this research project. Now, this is a major research project at the University of Alberta that's bringing together hundreds of our researchers. This is really all about developing the technologies that will make it possible for Alberta and Canada to meet its net zero energy goals. So I'm wondering if you might tell us a little bit about CANSES, why it matters, and what the future holds for CANSES and research at the University of Alberta.
Yeah, great. So, if you look at a lot of effort that we have had, I mean, U of A is a leader in energy. We have been doing energy research for decades. And we have, in fact, the oil sands industry, we have helped the oil sand industry develop over decades. And this has developed a lot of critical mass here, a lot of people who have expertise in various aspects of energy. Now, there is a need for decarbonization. We are aiming to basically achieve net zero emission by 2050. And what we, as a university, what we are trying to look at, what are those baskets of options which makes more sense, which can have bigger impact? And so in CANSES, you see there are 5 pillars in CANSES. The first one is the hydrogen pillar, where we have more than 65 people working on hydrogen and various aspects of hydrogen value chain. You look at hydrogen production, transportation, storage, and utilization. And so, that pillar is developing technologies and commercial scale technologies and addressing the challenges of developing hydrogen economy, various aspects of that. The second pillar is on carbon capture and storage. So we have more than 35 folks who are working on various aspects of carbon capture and storage, where we are developing these technologies to capture CO2 and sequester it. We are also working on taking this CO2 and producing materials or fuels through this, so utilizing that CO2. You think about the other key piece is all the decarbonization that we talk about. A lot of the electricity or renewable electricity, these are intermittent, as I talked about this in my presentation. So you produce it, but you can't, like wind and solar, these are intermittent, not available all the time. What you need to store the energy when this is not available. How do you store the energy? There are different options of the storage, but battery is one of the key aspects and key component of battery storage. There is a lot of work going on in battery, but the batteries need minerals. They need critical minerals. They need lithium. They need other materials. So the challenge is in terms of developing these technologies to produce cost effectively lithium from different sources. Our critical mineral team is trying to work on a lot of these technologies. And so that kind of, is our third pillar. We also working on a lot of reclamation and water impacts and developing technologies which can help us in providing, more efficient use of water. And that's the key piece. And then the other last pillar is in terms of all these electrification of the different demand sector that we talk about. So a lot of focus on EVs, a lot of focus on development of microgrids, smart grids. So a lot of technologies are being developed at U of A under that pillar. So if you look at the whole 5 pillars, we will have probably more than 200 people and 200 faculty members working on developing these net zero solutions. And that's what CANSES is about.
Yeah, and we're definitely Canada's leading research university on energy and developing net zero energy solutions. and I'm enormously proud of the work our colleagues are doing. I wanted to chat with you a little bit about hydrogen. And Amit, you'll recall when we went to India, and Amit is a great supporter of our outreach to India and our research collaborations and academic collaborations in India. And we had an opportunity to go there. And this was a lot of fun for me because I got lots of time to spend with Amit and ask him a million questions about energy and his research, and in particular about hydrogen. And you'll recall we were in the Mumbai harbor, and we were looking at all the ships out there, all of which are burning diesel, and of course there's significant CO2 emissions. And I asked you, well, is it feasible that all of these ships could be fueled by hydrogen? And how would we get that hydrogen? And one of the things is, the miraculous thing about hydrogen is when you burn it, its only emission is water. There are no CO2 emissions. But hydrogen is actually very hard to produce. It's energy intensive to produce. Unlike fossil fuels, you can't drill a hole in the ground and find hydrogen, except with a very few exceptions in the world. Hydrogen is also very complicated to store and transport. And it's also very volatile. And I've learned that it's also very corrosive in terms of transportation. So I'm curious to hear about the research that we're doing around production, storage, and transportation of hydrogen. And I know we've talked a lot about the tremendous natural gas resources in Alberta, which are basically limitless. And if we could use natural gas coupled with carbon capture to produce low hydrogen with very low emissions, and if hydrogen does become an important part of energy future, both in Canada and around the world, and I was recently just in Tokyo, and I can tell you there's tremendous interest in Japan around hydrogen. Japan is one of those countries that has no energy resources. It has no capacity other than nuclear to produce its own energy. And it's very nervous about nuclear, given the earthquake zone that Japan is in and its own experience with nuclear. So it's really looking for options around its own energy security. Unlike Canada, where we are blessed with all of these energy sources, Japan is not. And so I know they're very interested in hydrogen. So I'm curious to hear about a little bit more about hydrogen, the complexity around storage, transportation, utilization of hydrogen. I mean, this is a big, complicated project. And as you mentioned, it's not a destination. This is a journey. And one thing I just wanted to mention before I turn it over to you is there's a course I wanted to recommend to our listeners or our viewers today called 21st Energy Transition in the 21st Century. How can we make it work? And this is a free online course offered by the University of Alberta. And I wrote a little article about it and with a link to the course, and you'll find that in the chat. And I'm a law professor, so I'm not an engineer, and so this is all news to me. And so I took this course. I signed up for this online course. I learned a great deal about the complexity of energy transition, one of which, of course, was hydrogen. So with that, so for those of you who are interested in learning more, and if you're like me, not an expert in the field, I'd highly recommend this course. As I mentioned, it's free, done by one of our U of A colleagues. Really excellent, thoughtful discussion about energy and energy transition and how do we achieve net zero by 2050, and how do we do that in a way that secures that reliable, secure access to energy, and particularly given the growing demand for energy, as you mentioned, Amit, in your opening remarks. So I'm sorry, that's a very long question, but also I'll turn it over to you. Let's chat about hydrogen.
Yeah, and I wanted to say that, hydrogen, and then there is a renewed focus on hydrogen. So hydrogen is not new to us. Hydrogen, as I said, we have been producing hydrogen for ages. If you look at Alberta, I mean, we use hydrogen in our oil sand industry um, since decades for upgrading bitumen and producing synthetic crude oil. We produce it on a very large scale, 350,000 tons a year plant. I mean, these are large scale plants. Just to give you a comparison is in terms of, if I look at hydrogen plant, one natural gas based hydrogen plant, 350,000 tons. If you have a wind farm, which is 160 wind turbines, each of 1 megawatt, the amount of hydrogen that you could produce is not even 1/10 of that. So the challenge is much bigger is in terms of when we transition this. And so in Alberta, we do have the capacity to do this. See, there's a lot of focus now on hydrogen because it provides, it's multifaceted. So in terms of, not only as a fuel, yes, you burn hydrogen, you produce water, basically. But then if I want to have more renewables in the grid, let's say wind, solar, this is an option where I can store hydrogen. We talked about battery as a storage, but hydrogen can be used as a storage medium. You can store this and you can transport this. See, you can't transport renewable electricity unless until you build pipelines or the transmission line from one jurisdiction to another jurisdiction. This allows you to do that between different continents. So you could transport even the renewable electricity in form of hydrogen from one continent to another continent. Key piece. The other key aspect is if you look at some of these emission-intensive industries, so iron and steel, cement, there are some options of mitigating their GHG emission, but hydrogen provides an option for decarbonization because it can get them to the higher temperature. I mean, the challenge in terms of electrifying these is much more. So some of these industries, you can't go through electrification. So hydrogen provides an option for decarbonization of these emission-intensive trade-exposed industries. A lot of work that we have been doing is in terms of, we have researchers, as I mentioned, in terms of each of these pillars. So you have hydrogen production, hydrogen transportation, storage, and utilization. We work on different aspects of hydrogen production. So a lot of focus on producing renewable hydrogen from solar, renewable hydrogen. For any of these renewable electricity that you have, you need to take that and pass it through an electrolyzer with water as a feedstock to produce hydrogen. A lot of our researchers are working on various aspects of electrolyzer, improving the efficiency of the electrolyzer. How do you reduce the cost of producing hydrogen through electrolysis? So a lot of focus in that aspect. There is also a lot of focus on producing blue hydrogen, but blue hydrogen not only through SMR, we continue to work in improving the cost of production through SMR through development of different catalysts, but we also work on taking and developing different pathways of using natural gas to hydrogen. For example, methane pyrolysis. So we have researchers who are working on basically producing hydrogen through methane pyrolysis, heating methane, and then producing hydrogen and then solid carbon. So you don't have to go through the whole process of carbon capture and sequestration. There would be some CO2 emission, but majority of the carbon is in form of solid carbon. So they are developing technologies so that this can be implemented on a decentralized scale, but also on a large scale. So, there are other work in terms of the production piece. There is also a lot of work on looking at the materials, because as you mentioned, hydrogen has challenges in terms of the material. If you want to build a hydrogen pipeline, you need to have a specific hydrogen pipeline, because the typical natural gas pipeline, there would be challenges in terms of embrittlement of the pipeline. This is corrosive. So there is a lot of focus on developing these new material. Now, in terms of you can transport hydrogen in form of gas, in form of also you transport gas, but from one continent to another continent, you liquefy it and then transport it through the tankers in form of liquefied hydrogen. But there is also a lot of focus in terms of the hydrogen carriers. So you have ammonia, you have methanol, you have liquid organic hydrogen carriers. Liquid organic hydrogen carriers are very much like crude oil. So you can transport it through pipeline. So there is a lot of focus and research where we are working on various aspects of producing efficiently these different types of energy carriers. And then you come to the utilization piece. I mean, you use hydrogen in fuel cells, for example. So a lot of focus on developing these, enhancing efficient fuel cells, different types of fuel cells for cars, for buses and heavy-duty fuels. So these are kind of heavy-duty vehicles. So these are all there is a number of researchers working on the fuel cell piece. We also have researchers who are working on using the same internal combustion engine, but co-firing hydrogen with our fossil fuel, what we use. So, there is, if you look at the whole chain of hydrogen, production, utilization, we have researchers working on each and every aspect of this. In addition to these, we have folks who are working on hydrogen value chain enablers, I call it. So enablers is not only in catalyst, it's a lot of process optimization. We look at a lot of these safety issues in various aspects of hydrogen value chain. We have folks who are working on also developing these enhanced models, which are sensors, I should say, for various, again, unit operations for hydrogen. So it's a big, large group and a critical mass at U of A, basically working on hydrogen and various aspects of hydrogen.
I'm wondering if you might comment on what potential hydrogen holds for Alberta's economic future. Because one thing you mentioned, Amit, is that oil and gas is bread and butter here in Alberta. It has built much of the wealth that we have in Alberta. And as you mentioned, a lot of the research supporting the oil and gas industry has been developed by the University of Alberta. Does hydrogen hold similar potential, economic potential for Alberta in the future? And if so, how can we make that happen? And how is the research being done at the University of Alberta helping to support that?
Yeah, great question. See, if we look at Alberta, so we have crude oil. We export bitumen in form of bitumen or probably synthetic crude oil, those two forms. We also have a lot of natural gas. If you look at the natural gas export, it has gone down. We used to export, like we export, still exported to US, but the export for natural gas has gone down. So what is the alternative to convert that resource into a form which world wants? Now, hydrogen provides an options for us. Now, it's not something that we have not done. So we have large source of natural gas, large potential of natural gas. We know how to produce hydrogen because we have been doing it over decades on large scale. The CO2 that is there, like that is emitted during the production process, we can capture and sequester and put it underground. We have large infrastructure like Alberta Carbon Trunk Line, capacity of 14 million tons of CO2 transport per year, which is huge. And then we are blessed with the geology also where we can sequester CO2 in our, underground, where it is much benign to sequester these. And so if you look at all these resource, know-how, the geology, the infrastructure is there. And then we do have workforce who has been working on producing hydrogen on a large scale. And that's a win-win. Compared to this, if you also try to marry this with what the other side of the world has. So for example, Japan. Now, Japan, they are net energy importer. They would like to decarbonize, but what are the options? If they import a lot of LNG, they use LNG, but then they emit CO2. Now their geology does not allow them to sequester CO2. So they have to export CO2 outside the country to sequester or find a way to handle that CO2. And so they would like to look at something where they don't have to bother about CO2. So hydrogen provides an option. And there is a lot of focus on getting hydrogen and in using hydrogen. So it's kind of a perfect marriage in terms of we have the know-how, we can produce what the world wants. And that kinds of, a big opportunity for us. And then to support that and to support the industry itself, as the industry develops and as there are more production plants, more utilization of hydrogen increases, we have the know-how and the university where we have the researchers who can not only work on the development of the technology, but through the whole chain of technology development to technology commercialization, and then address the challenges that the industry faces in terms of going to a larger scale. We are already doing it. And that's another big opportunity for us to actually develop this economy together. So it is a big opportunity for us globally and become a global leader.
Because one thing we host here in Edmonton is an annual hydrogen conference, which I think 5 years ago was a small affair, and now it's just growing in leaps and bounds and is literally growing by thousands of new participants every year. And this, I believe, will take place in May. And U of A has a big presence at this hydrogen conference. And I know when we're chatting with a number of Japanese industry partners, they're all coming to Edmonton in May to come to the hydrogen conference because they want to learn more about hydrogen, what's happening in Alberta, and the research happening at the U of A. Amit, I'm wondering if you might comment on the timelines here. When might you see Alberta being in a position to be exporting large amounts of hydrogen to countries like Japan? How long would it take to develop the technologies, build the infrastructure, build the ships, the pipelines, uh, I mean, this is a big job to make all of this happen. So I wonder if you might give me a sense of the timeline.
Yeah. So in terms of this, like, the production piece is already there in terms of we produce hydrogen, we can produce this. We do have infrastructure, and the new plants are coming. So you see Air Products hydrogen production plant coming this year, and commissioned this year. There are other announced plants which is coming in. To get to Japan, we need to develop more infrastructure, and especially the form in which we can transport our hydrogen from Alberta to the coast. Initially, it could be in some of the form of some of the carriers. So, for example, ammonia. A lot of focus on ammonia, maybe methanol. But these in form of those could be transported by rail also. We do ammonia transport by rail. So as we transition to these exports, maybe initially it would be mostly by rail, but then you develop infrastructure where you get dedicated infrastructure to transport hydrogen. So if you look at the goal that the government has set in the Alberta Hydrogen Roadmap, we do plan to export the ammonia and hydrogen in form of ammonia by 2030. So it's not that far in terms of when we are able to transport hydrogen to Asia Pacific countries. I think you will see this happening within next 5 years.
In the next 5 years.
Yeah.
So this could be a whole new energy future for Alberta.
That is, yes, it has a significant potential, and to basically transform our economy and kind of generate the wealth that oil sands has done.
Because as you mentioned, we're uniquely situated because we have vast quantities of natural gas, and we also have the geological capacity to store carbon.
That's right.
And
Yes.
there's not a lot of places in the world that have that magical combination.
No, if you look at, I think there is not, there are no places. In fact, when you combine your resources, your capacity to build on large scale, the know-how, the workforce, the infrastructure to sequester carbon, and then the geology to sequester that carbon, all of those ingredients you won't find around the world. So this is a unique opportunity for Alberta.
It's the Alberta advantage.
That's right.
One of many. And again, much as we did with the oil sands, we're driving the research that is going to make this possible.
Yes, and we have the critical mass to do this. And I especially say this because we have critical mass, the various aspects of the hydrogen value chain. And that kind of large critical mass, so any challenges that the industry is facing or is, any kind of technology development or commercialization, there is critical mass here to support that kind of development. And so, it's a kind of very win-win situation for both of us.
And when I went to Japan, I went with our colleague John Vino, and as you know, he's working on a research project to produce hydrogen using a catalyst. And I wondered if you just might comment on that. I mean, I was fascinated to hear about his research and the potential that holds to enable another way to produce hydrogen that would be at a low cost and make hydrogen readily available.
Yeah, potentially. So what he's working on, and probably, he could talk more on this, but
Yes.
the way I understand is more developing these catalysts to produce hydrogen from water.
Yes.
directly. So that could reduce the cost significantly because you might not need other infrastructure to produce hydrogen. So that's kind of, again, the technology at initial stages, but it's coming up faster.
Yeah.
So, those kinds of technologies and examples are there at U of A, number of these technologies which are being developed. So we
Yes.
are kind of at the forefront of, hydrogen economy and the type of work that we are doing.
And I'm curious if you just might talk a little bit about your academic journey. How is it you came to be interested in energy and hydrogen and your journey to the University of Alberta?
So, I have an undergraduate degree in energy engineering, so which is pretty unique. You don't get a lot of undergraduate degree in energy. But that's from India, and that was at IIT Kharagpur. I did undergrad in energy, so I had a kind of desire to continue to work in energy. There was a lot of kind of people get the undergraduate degree, but they move on, and there was a lot of movement to the IT sector and all. But I wanted to continue to work in energy. Um, if you have to be working in an energy jurisdiction in North America, there are only two places that you will go. Either you go to Texas or Alberta.
And Alberta's better.
So, in terms of, and then there was an opportunity to work on the decarbonization pathway. I had worked on decarbonization pathways and assessing that for developing country. I did my master's at the AIT in Asian Institute of Technology in Thailand. There, we were working on decarbonization pathway for Vietnam. How can Vietnam decarbonize their sector? And so it continued from there and looking at Alberta and the opportunity that was here. So I came here and did my PhD and then continued as a faculty member from them. And as I said, at that time, decarbonization pathway, energy system concept, a lot of assessment. Well, people used to hear that, but it was not a priority. It was not the focus. And then over last 15, 20 years, it's also, it's nice to see that the thought process has shifted. We have been able to create a niche area where now the people look at it, everything through an energy systems lens. We talk a lot about decarbonization. We talk about how the assessment of these decarbonized pathway is critical for decision making, for investment decision, for policy decision making. For hydrogen, we started working on hydrogen in 2009 and 10 through a grant from Alberta Innovates, where they wanted us to evaluate how do we produce hydrogen from underground coal. These are unminable coal at that time. So we used to produce power from coal, but these are unminable coal underground. So we wanted to look at, we can probably gasify coal underground, produce syngas, and then separate hydrogen from syngas, sequester the CO2, and produce hydrogen. That was the beginning of that. After that, we continued to work on hydrogen and various pathways, wind, solar, biomass, natural gas-based pathway, and then it picked up. One of the role that university plays is always looks ahead, look across the bend, what is there. And I think what we are working on today, I mean, some of these technologies are pretty early today, but 5 years, 10 years down the road, those would be game changers. So that has been kind of, the way it has grown. And now, we work in energy, and this is what I do. Energy system assessment and energy pathways, looking at various ways for decarbonizing.
So you're a wonderful example of an enormously talented international student who came to do a PhD at U of A and decided to stay to our great good fortune and join the faculty. And I'm wondering if you just might comment a bit about your own students. And I know that you draw students not only from across Canada, but around the world, and just a little bit about your commitment to your students and how you engage with your students. And I'm sure our alumni listening would like to hear a little bit about our students today.
That's the best part of this job, I would say, in terms of having discussion with the students, working with the students. I mean, the students are the drivers. They are the wheels who drive your car, basically. We have, in fact, I have been lucky in terms of having students. We have had probably more than 35 countries represented in our group, where students coming from all the different parts of the world, and they work on various aspects. I mean, the key that I think is that when these students come, they invest a lot of effort in coming here, and here then and with support from university. I would say university has been great in providing support continuously for developing these research programs. And then these students who have now, like, a lot of students have come in, more than 200 have passed through the program. And they have worked on different sectors of economy, and its energy sector. They are now contributing all across the globe and across different sectors. They work in the federal government, provincial government, municipal government. They work in the industry, large industry in Canada, outside Canada. A lot of them have become faculty members around the world. So, they are basically kind of spreading and training the new generation of engineers, what we have started 25 years ago.
Yes, well, I think our time is drawing to a close, but Amit, I wanted to thank you for taking the time to chat with us this evening. As you may tell, I always greatly enjoy our conversations about energy and research and the great work happening at the University of Alberta. We are so lucky to have you at the U of A as a colleague, and I know that you're so generous and giving to the university, and your commitment to your students and the tremendous research that you're doing and how important it is. So I just once again want to thank you. Our next President's Speakers Series will be in October. We'll be doing this in person. And so stay tuned. I always really enjoy these conversations. Once again, I just want to thank all of our alumni and supporters who have joined us this evening. And it was great to see so many of you from all over Alberta and Canada and really around the world. And so with that, once again, thank you, Amit. I look forward to more conversations, and we'll be signing off. Thanks, everyone.